When it comes to calculating the area of hexagons, most of us are given the formula that the area is to be calculated by squaring the side length of the hexagon and then multiplying it by a coefficient of 2.59. And many people ask me in the class, just what the heck is 2.59? Where does it come from? Who figured that 2.59 there? In this video I'll show you what this is. I'm going to walk you through step by step what it is and where it comes from. It's going to be an adventure. First off, before we set out, the 2.59 is an inaccurate number. It's an approximation and doesn't give you the exact area of the hexagon. For example, if this hexagon has a side length of 5, if that number is 5, then this formula would require you to go 5 times 5, that's squaring the 5, the side length, and then multiply it by 2.59 equals 64.75. And this can be square inches, square meters, or square centimeters, whatever you like. I'm going to leave a unit of measurement out consistently. Just concentrate on the numbers and watch my hands because I'm cheating. So with the formula, the area of the hexagon is 64.75, and I say inaccurate. I'll show you why. The hexagon can be broken up into two trapezoids. You can, if you like, calculate the area of the trapezoid. Remember that the side length was 5, so it's 5 everywhere, and in the middle it's 10. How do I know that it's 10 in the middle? I'll answer that in a sec. If you want to use the area of the two trapezoids, you calculate 1 and then you just double it. You have the area of the hexagon. But to calculate with the area of the trapezoid, you're going to need to grab the longer base and the shorter base, add them together, chop it in half to average them out, and then multiply it by the height. And the height of this trapezoid would be here. That would be the height of the trapezoid. You don't have that number, you have to get that number. You're going to have to do trigonometry with it. So might as well break it up into triangles. And by the way, that's how I know that the base of the trapezoid is 10, because a hexagon breaks up very nicely into 6 equilateral triangles. An equilateral triangle means that all of the side length, what was originally the side length of the hexagon, and it's 5 there, it's the same side length for the triangles. Equilateral means equal side length. So there you have 6 triangles, and what you need to do is calculate the area of one triangle, and it just times it by 6. Now to calculate the area of one triangle, nothing simpler than that. You grab the base, in this case it's 5. Now the side length, notice that the side length became the base. What is the side of the hexagon is the base of this triangle that I singled out. And I'm going to use the word base from now on, but it's the same thing as side for the hexagon. But as it relates to this triangle, it's a base. And that was 5, that was 5, that was 5, and there's the height of the hexagon. Height of the triangle running down there vertically. I do want to point out that that's a square corner there. So we have here the height perpendicular to the base as per standard procedure, okay? In the middle here of this TIE fighter, because that's what it kind of became, in the middle of the TIE fighter you can see this circle, and in the circle we have 360 degrees if we want to use degrees for measuring angle of turn. I do want to use degrees, and you notice there are 6 little triangles that meet in the middle. So the circle here has been divided into 6 slices. That's a super mini pizza here. If a circle with 360 degrees is divided into 6 little pizza slices there, that being 1, 2, 3, 4, 5, 6, that means that each pizza slice has a central angle of 60 degrees, because 6 times 60 is 360. So each little triangle has a 60-degree angle, and since this is an equilateral triangle, it is a 60, 60, 60 triangle, because, and I'm not gonna detail it why, the sum of the internal angles in any triangle is 180 degrees. 60 plus 60 plus 60 is 180. Just take it from here. So we have ourselves these triangles, this 60, 60, 60 equilateral triangle, which has a side length of 5 in every direction. One of the 5s have been singled out to become the base of this triangle that we're going to calculate. We can't really calculate the area of the triangle without the height, because it's base times height divided by 2. That's how you calculate the area of this triangle, any triangle. There. Oh, that's ugly, I'll fix it. Just a sec. Area of this triangle. Maybe with my left hand. There we go, that's better. And so for this one we need a base. How we get the base is gonna need trigonometry in it and trigonometric functions. And I mean sine, cosine and tangent business. If you need a refresher on that one, go for it. I'm gonna apply it right away here with minimal explanation. What I did with this triangle is I cut it in half, and it became this half of a triangle, which is also a triangle. It's a right angle triangle, like I said. It's important because the trigonometric functions of sine, cosine and tangent apply to right angle triangles. In trigonometric functions we have terminology, opposite and adjacent sides. And that requires that I rename the base and height yet again for this purpose with the opposite and adjacent terminology. So I merge the two. It's gonna make sense in a sec. Do notice that when I cut the equilateral triangle in two, that 60-degree angle became a 30-degree angle there, okay? So the trigonometric functions that can be used here, let's see, are these ones. You can either use the tangent function and relate it to the 30-degree angle, in which case tangent 30, I just add in the circles there for the degree. The tangent of an angle is, if you remember this little memory jogger, soka, toa tangent is opposite over adjacent, so opposite over adjacent, and the opposite side in relation to this 30-degree angle is the base. So the base now also became half of its original base, because I cut the original equilateral triangle in half. So I have a new base, and this new base is what I'm going to refer to as opposite side. That's not a zero, that's an opposite side, because this is the angle and that's the side opposite that angle. The height becomes the adjacent side. Adjacent means next to. So that side here, the height, is next to the 30-degree angle. So you can also use the cosine function if you like. I encourage you to try it and give it a go. It's going to be the same calculation done a little differently, but you should get exactly the same result. So because base is the opposite side and the height is the adjacent side. The height, therefore, and I'm going to use the tangent formula with it. The height was, see, okay. The height is the adjacent side, so the height comes here, and the opposite was the base. That was the 2.5. It was the 2.5. From this equation, the height of the triangle is base, or 2.5, divided by tangent 30 degrees. When you enter that into your calculator, you are gonna get a number which looks like 2.5 divided by tangent 30 equals 4.33, and there's more digits to it. It's on the calculator's display. I'm just gonna write it down that the height, let's go, that this height is 4.33012, and there's more digits to it. So this height here is 4.3, I saved it on the calculator's display, 33012, and this base here was 2.5. So what we need to do is base times height divided by 2 to get the area of any triangles. And I'm going with this triangle, and if we're going with this triangle, there's 12 of these that make up the big hexagon, okay? In that case, the base is 2.5, and I'm going to multiply it by, the height was 4.33. It's still on my calculator's display, so I'm just going to multiply it in a sec. I'll just fix that one because it looks a little lame. And then we're just going to be dividing by 2. Let's see what happens to this triangle, the area of that chopped in half equilateral triangle. If I do this number by 2.5 equals divided by 2, I'm gonna get 5.412 plus the rest of the digits. Don't get rid of the rest of the digits, because now I need to multiply it by 12, because there's 12 of them that make up the hexagon. And if I do so, I get the number 64.95190528 for the area of the hexagon. That's the full hexagon. Now if you remember, going back to slide 1, we calculated that the area of the hexagon was 64.75, and I said imprecise, inaccurate and incorrect, because the 2.59 is a truncated decimal number. There is more digits to it, they just chopped it off there. Sometimes you might get a 2.6, and lo and behold, when we calculate the area of the hexagon using standard trigonometry, it's not, it's more than that. It's not 64.75, it's 64.95. There, 75 there, and up there, where were we? And 95 there. So that's why I said the formula is kind of works, but it's a little too simplistic. But where the heck is 2.59? We still don't have 2.59. Okay, I'll show you what 2.59 is. What we did here just now is we multiplied the base with the height of the small triangle, of which we have 12. We divided by 2 and then multiplied by 12. Now instead of dividing by 2 and multiplying by 12, we might as well instead just multiply it by 6, right? Instead of chopping it in half and multiplying by 12, we just multiply by 6. So we did base times height times 6. Okay? Now for height, we had an interesting equation, something to do with tangent in it. And it was actually, the 2.5 was divided by tangent 30. And so we took the base, we multiplied it by the height, which was calculated by 2.5 divided by tangent 30. which was on this slide here, there, 2.5 divided by tangent 30. So there's 2.5 divided by tangent 30 for the height, base times height, times 6 because that 6 is still there. If I do the numbers this way, multiply the base, which is 2.5, times 2.5, because we went 2.5, we went with the smaller triangle, of which we have 12, okay, but we got rid of the divisor 2 and 12 became a 6. So 2.5 times 2.5 times 6 is 37.5. When you get the 37.5 and divide it by the same tangent 30, you're going to get 64.95, the same number as we got here when we calculated the area of the hexagon. 64.95190528. There, 64.95190528. Same number. Now, so where is the 2.59? Coming up right this moment. If you take this number, this 64.95, and divide it by the side of the hexagon, which was 5 squared, which is 5 squared is 5 times 5, 25. You divide the actual area of the hexagon with the square of its side length, there's your 2.59, and the rest of the digits. Because it's got more digits, it's not just 2.59. That's why the simplistic formula that you're given, and looks like that, is going to give you an inaccurate answer and an inaccurate number, because it's got, because it's got more digits to it. To recall all the numbers in this decimal accurately, here are a couple of ways you can go about it. You can use the cosine function. If you just enter on your calculator 3 times cosine 30, you're going to get that number right away, and your calculator will have 20 digits in the decimal, not just the ones that are on the display. It's got more digits in the memory bank, so your answer will be highly accurate. 3 times cosine 30 or 3 times sine 60. And here is my challenge to you. Try these ones and try to show them where these numbers come from. Going back to this page here, work with the 30-degree angle here or the 60-degree angle in this corner over here, because it's a 30, 60, 90 triangle, and relate the cosine function, or work with the 60-degree angle and work with the sine function, and work out the details where these come from. We used something like this, but instead of 1.5 we had another number up there because the side length was not 1, the side length was 5. So if you enter that into your calculator, you're going to get the same number, and 1.5 times tangent 60 will also give you the same magic number for the hexagon. So that's what the meaning of that 2.59 is. Again, one last time, I'm not insulting your intelligence. 2.59 means that in any hexagon, let me just draw you a hexagon here. In any hexagon, the square of the side length, in any hexagon, the square of the side length is 2.59 times smaller than the full area of the whole hexagon, or the other way around. The full area of the hexagon is 2.59 times bigger than the square of the side, if you square the side length. Okay? That's the meaning of the 2.59, and that's where it comes from. Fairly straightforward. A little bit tricky though.